we go. Let's talk about domain, range, and intervals. Anybody watch the little video? Okay, if you watch the little video, boom, this should be good and easy. Anson watched it. Nice job, Anson.
Does it tell
Okay.
you watched it?
No, it doesn't. Oh yeah, then I watched it. Yeah. Is that what you're gonna say?
No. I was just wondering.
Yeah, it does. Okay. So here we go. Let's talk about domain, range, and intervals. So functions, we're laying our groundwork for functions, okay? And so when we're working with functions, we need to describe sets of numbers. So we're going to talk about how we can describe sets of numbers here. Okay. We have domain, which we talked about. A domain is a set of all possible inputs. Those are all things we can put into our function. All right, Alan? Okay. Okay. All right. Let's focus on domain and range here now. So range is a set of all the outputs, all the things that can come out of a function, right? And when we have a function, we can't always get any number out. Sometimes we can only get certain numbers out of the function. And likewise, sometimes we can only put certain numbers into a function. Okay, so we're going to start off talking about some number families here. So let's get a little situation to give us some perspective. Okay, so daily temperatures. All right, suppose we're going to record the average daily temperature for some place, maybe it's Grants Pass, okay, or in some particular city or location. Okay, we're going to record it for a year. What are the two variables in this situation? We're going to record the temperature for a year. What's the two variables?
We do the temperature and
Good.
the date.
All right, so we're recording it, average temperature for every day, right? So we have time or days and we have temperature, right?
So you would say time and then temperature.
Sure, you can say time, yeah. Okay, temperature. So those are our two variables there. All right, so days and temperature. All right, which one of those is the dependent variable? Which one, ask yourself this question in your head, which one depends on the other? Does temperature depend on the day of the year, or does the day depend on the temperature? Temperature depends on the day of the year, right? It's colder on certain days than others, right? Does the day of the year, whatever day it is, care about the temperature outside? No. Today is the 18th, no matter what the temperature is outside.
It's cold, it's not gonna be
Right?
It's cold, so it's got to be the 19th. Sorry, pal. Like, that's just
Okay.
how calendar works.
Now, it may not be a perfect predictive function. If you can come up with an equation that predicts the temperature, you're going to be pretty darn rich, okay? But it's a little more difficult than that. So the dependent variable is the temperature, okay? It depends, the temperature. The independent variable is the days. All right. So let's think about this. What are all the possible numbers for the independent variable? The domain. What kind of numbers can we use for the independent, which is the days? 1 through 7 days of the year. 1 through 365?
Yeah.
Can we use 1.5?
No.
No. We're not going to say on day 1.5 the temperature was, no. It's day 1, day 2, day 3. Are we going to use 0?
No.
No, in this case we're probably going to start with day 1, right? The first day we collected data, the second day, right? Okay. So the possible temperatures are 1, 2, 3, 4, 5, and 360. What if it's leap year? It could be 366 if it's leap year. Okay, so we'll go with that.
365.25.
Okay, what's the possible numbers for the dependent variable? Temperature. Okay, so we got the temperature.
I would say, I mean, technically it could go on forever. I mean, it's not realistically going to be like a negative 1,000 degrees, but there's nothing to say it can't.
Okay. So Mary, can we have, are we talking about numbers like the days, 1 degree, 2 degrees, 3 degrees, so on and so forth? Now what's a little different about temperature?
They can be point degrees. You're not going to get like 1/5 of a day in 24 hours.
Okay.
That's possible.
So we could have 1.5 degrees or 7 degrees or, you know,
But you
right, 100 degrees.
Real
Okay.
number.
all real
Okay,
numbers.
maybe all real numbers. Okay, oh, here's an interesting question.
You can have negative numbers.
Could it be, is the temperature ever pi degrees?
No.
Pi is the number 3.14159, so on and so forth, right? Now, hold on.
All
So think about this, wrap your brain around it. During the year, does it ever freeze in Grants Pass?
Yeah.
Yes. And so it gets down to 0 degrees Celsius. Freezing at 0 degrees Celsius.
But it also gets
Right?
Right.
And right now it's obviously not freezing. So sometime between now and the first time it freezes, will it ever be pi degrees?
Yes.
From moment in time, as the temperature is going from 4 degrees down to 3 degrees, at some fraction of a time, it is 3.1415926.5, blah, 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 exactly that number. Okay? You're not going to realize it, but it happens. Yes, Ansel.
But energy is quantized, isn't it?
Yeah.
So you kind of,
But he's not a scientist.
This
Oh,
is
you
the
don't think it's
question.
continuous?
well, yeah.
You think it's discrete?
Well, you know how energy kind of jumps?
Sure.
So it probably just, I mean, it wouldn't be able to go all the way.
It would be also.
Okay, so can that temperature, so at some point, so you're saying, you're saying that that's what we call discrete and not continuous. Okay, interesting thought. Okay, so,
I think what he was
yes.
trying to say is that it is possible for the temperature to be 3 point. It's not going to probably. Get
Okay,
there.
but no, but Anson is making a good point because pi is infinite,
You got a point.
and if what we're saying by quantized, because the electrons are jumping and they're releasing a certain amount of degrees, and that is a set number. Okay, so you're saying that it can never be infinite. Great thought, I like it. But let's leave it at that. Can it be negative degrees?
Yeah.
Yeah, okay, -2, so on and so forth, okay, negative pi, okay, all right. All real numbers is kind of the idea. Can it be negative 500 degrees?
Yes.
Scientists? Can it be negative 500 degrees Celsius?
Yes.
Yes.
No, we have something called absolute zero.
Oh, yeah.
Oh,
Negative
geez.
273.15.
So what
Okay,
it is to write down.
okay, just leave it at that for now. The point is they can be decimals. All right.
Okay.
Here's what I want you to think about now. I'm going to turn over your group and see if you've heard of some of these numbers before. We have groups of numbers, natural numbers, whole numbers, integers. Okay, and what I'd like you to do is write down the first numbers in each of these number families. If you need to research a little bit on the internet, go right ahead. Okay, so take 2 minutes, see if you can write down the first 3 or 4 numbers in each of these families. Okay?
What?
Go for it. Some of you may know, some of you may not.
Well, it's actually 3, 4, and you can just keep counting. Whole numbers are the same as
So basically, natural numbers or
Those are the numbers that we learn naturally with our kids. What's the first number? 2? 0? Oh, is it 0? Okay, 2. Zero's a weird thing. It's like, right? So it's kind of a weird thing. Usually it's not. When you can talk when you're about 1 year old, the first thing you use most kids say, I'll try. And then they say, then it's 3. And then after a little while, they learn this number. Zero's kind of a weird one. The natural number is 1, 2, 3, 5. Integers you should know.
You said it.
Okay, so we've got a vocabulary. What are natural numbers?
natural numbers.
1, 2, 3, 4, 5, 6, 7, 8, 12. Those are naturals.
Yeah, true. And some
Used for counting.
First fraction, 1, 2, 3, 4, 5.
Yeah. Whole numbers are just any number besides decimals.
Those are the number.
I do think you're actually fractions and decimals. Yeah.
That's one that comes. What do you think? 1, 2, 3, 4, 5 are integers with this other.
Yeah, that's right.
Okay. All right, so let's see what we came up with.
It's so cheerful and positive.
Natural numbers. Okay. What in the world are natural numbers? Gals up front here, what are they? 1, 2, 3, 4, and 5. Okay? Natural numbers are the numbers that you naturally learn when you're a kid.
So
First number you usually learn is 1. I'm 1 years old. That's about when you start to talk. Okay? And then you learn 2, 3, 4, 5. Okay? Those are natural numbers. Okay?
How long? Just those 5 numbers, or does it go on?
It goes on forever.
Oh,
Yes.
okay.
Yeah. Starting at 1 and going up to
Okay.
going up to infinity or towards infinity. Okay.
I just had to make sure.
Just had to make sure. All right. Dot. Have I showed you a little side note? Speaking of notes here, have I showed you how to cut things easily with the arrow? Real quick side note, because this makes your life a lot easier. Okay. If you did something, let's say you just wrote. Okay. Can you see? There we go. Okay. So, if you had written down here 0, -1, -2, those unfortunately are not all whole numbers. All right. And just a little technique that I think will make your note taking easier once you get this is this arrow. Real handy tool. Okay. This is the stuff you can't do with pen and pencil. All right. And those 3 numbers there, sorry, they are not integers. So if you drag a little arrow around them, it selects them. And there's a little X right up there. It's not showing up. And there it is. Okay. And you can just X delete those. Okay? So it makes it real handy for moving things around and not rewriting stuff. And then you might say, okay, I want to move these over. That's okay. Select them. And just grab the little hand and move it over. Okay? Little tools are useful. And one more tool that's useful is this grouping one. Okay? So if you're saying, I need more room, we'll group it. Now it's a group. Hit this little double circle, shrink it up, put it in that corner. Now you have room for days. You can fit a whole book in this little box. Okay? All right? So kind of a little different way. Once you do it a little while, it's pretty slick and quick. I've been doing it for about 3 years now, and anyways, you'll get it, or you
won't.
Or you won't. Okay. So, anyways, there's some notes you can try that makes your life a little easier. So you don't just have to write and erase and write and erase. All right. So, anyways, back to the topic. What's a whole number? Natural numbers are kind of like the whole numbers, but there's one number that we need. 0. That's right. You know why 0 is a whole number? Because it has a hole in it. That's right. Okay. So we've got natural numbers that you've learned to count. We've got whole numbers there. What are integers? Alyssa, what do we need to add for the integers? You got it. 0, 1, 2, 3, ... and -1, -2, and -3, ... All right. So those are integers. And let me highlight those and move them because I want them in a different spot. Okay. Rational numbers. Rational numbers. What are rational numbers?
Rational numbers are numbers with a finite amount of decimals.
Okay.
Or they repeat.
Okay, good. Exactly. So they are repeating.
Or like
Repeating. You'll be able to fit this if you zoom in. And terminating decimals.
so
Maybe we
pi
should say
would not be
or.
a rational number. 'Cause it doesn't repeat.
No, it's irrational.
Now, what does
So it says-
rational, what mathematical word is in rational?
Right.
Rat. And ratio. Okay, ratio is also in there. What does ratio mean? Like, hey, I'll ratio across the street.
Like 1 to 1.
Okay. Okay, 1 to 1, 1 to 2. Okay, like with a colon, right? Or sometimes we write ratios as fractions. Fractions are ratios. So the technical definition for a rational number is anything you can write as a fraction of integers. 1/2, which by the way is 0.5 as a decimal. It ends. Okay? 1/4. It's 0.25 as a decimal, right? 1/3. Okay? What's 1/3 as a decimal? 333333333. But it's rational because we can write it as a ratio of integers. Okay. All right. So on and so forth. How about this? 0.175. Ooh, do you know what the fraction is for that? Can you write that as a fraction?
1/8.
I don't know. I can write it real quickly. I don't know what simplified is. It's 175 what?
Hundreds.
Close. Thousands. Okay. So yeah, any terminating decimal can be written as a fraction real fast. Okay. All right. And one more thing. We'll side note. This is just fun for fun. Okay. So if you're like, oh, that means I'm going to turn off. Go ahead. Okay. 0.9 repeating. Do you know what that is? Equal to? Good try. No. Oh, well, okay. You said. I'm sorry. You said. What did you say? 3/3. Interesting. Because 0.3 repeating is 1. So 0.9 repeating is 3 of those, right? Very interesting. Okay. I like that. Never heard that. Let me. Wait. That can't be possible. Make up your mind. Are you ready? Catch. Is it 0.9 repeating? Oh, so close. 0.9 repeating or 1. Okay, well, here's a quick proof, and a quick interesting proof, then we'll move on. Let's say that 0.99 is equal to x. I don't know what it is. Okay, let me move this. And if that's the case, then what is 10x worth? What's 10x worth? That would be 9, right? Because you move the decimal one place, right? 9.99, right? 99999, yeah. Okay. And so what we have here is a little system of equations. I'm going to move this down here. Uh-oh. Okay. Do you remember how to solve a system of equations?
Yeah.
What can we do?
You could substitute in 0.99 or
Yeah, we could substitute. That's a good way. It's a little quicker to subtract. Substitute is just fine. If we subtract, watch what happens. What's 10x minus 1x? 9x. What's 9.99 repeating minus 0.999 repeating? Oh, it's 9. Yeah. So these cancel out. It's 9. And so what's the answer?
X equals.
You get it. Okay.
X equals what?
X equals 1. So 0.9 repeating is just 1. Okay? All right. That's a side note, kind of an interesting curiosity. Okay, but we've got this. All right, we've got rational numbers. They repeat. Irrational numbers, they don't repeat. Okay? They're non-repeating, non-terminating. Okay? Okay. By the way, if I go too fast, you're like, I don't want to write that down. Feel free to copy the notes. I'll I'll put the notes up when they're done, so I'll post them on that page. Like pi. What's another irrational number? Square root of 7, square root of 2, square root of 5. Okay? They're all irrational. There's one more famous irrational number. E. We'll talk about the number E. It's like pi. Okay, last but not least, what are real numbers? Well, those are our rational and irrationals together. Rationals and irrationals. All right? That's the idea. Okay? Put all those together and you have our real numbers. Okay? All right, so those are different sets of numbers. And now we got to be able to describe groups of them, parts of them. What kind of numbers do we use for the days up here? What kind of numbers are those? 1, 2, 3, 4, 5, so on and so forth. They're natural numbers, right? Or they're integers. And by the way, notice we're going to use these letters for these groups. Mostly we're going to use the natural number, the integers and the real numbers. This R and that Z is what we use for reals and integers, okay? These are real numbers here. These are natural numbers. Let's jump to the second page there. All right? And let's think about this. What type of numbers can we use to describe the days? We just said it. We could use integers or natural numbers, right? Mm-hmm. Natural, or we could call them integers. Special integers, right? Not all the integers. We could call them positive integers. And so here's how we describe them. We got a couple ways, couple things. We've got this thing called set builder notation. Okay? Set builder notation means this. I really don't want to write out all the numbers. Okay, I want to tell you which numbers are possible, but I really don't want to write 1, 2, 3, 4, 5, 6, 7, all that, right? I'd rather just describe it. So here's how we're going to describe it. The set of all numbers that can be used for the days, we'll call it capital D. Okay, and here's how we write it in set builder notation. We say the days, the set of days are all the D's. And this little line means something. This little line means, if you zoom in, you can write such that. So we say all D such that D is greater than or equal to 1 and less than or equal to 366. Does this little part make sense? That should look very familiar, right? So it's all the D's such that D is in this range. And what else has to be true about D? It's an integer. What does Z mean? Integers. Okay? D. Why Z? I'm not sure. Okay? This little symbol right here means, as it says in the text below, it means is an element of. Okay? This is right there. Okay? So it means is an element of, and this little symbol there is red such that. Okay? We could also have said it's natural numbers as well. What type of numbers are the temperatures? What type of numbers are the temperatures? They are no. Temperatures can be lots of different things, right?
Oh, yeah.
Okay? Temperatures are real numbers, right? Because they can be decimal values. They could be pi, all right? So on and so forth. Square root of 2, things like that. Okay? And so we're going to describe it like this. Now, theoretically, we have absolute 0. Okay? And scientists say there's a maximum possible temperature of 10 to the 32nd. Okay? So we could say this. Temperatures can be anywhere between 273.5 degrees Celsius, supposedly, and 10 to the 32nd degrees Celsius. All right?
We don't know.
Okay. Yeah, exactly. I don't think we're going to be around to measure that. So we say the temperature is all T's such that T is between negative 273.15, but we can't reach it. because that's absolute 0. And 10 to the 32nd, okay? So, we graph, remember these graphs, these line graphs from Algebra 1? Probably. Okay? So this inequality is an open dot. What does that mean? Can't equal. Very good. And a solid dot means it can equal. Okay? So theoretically, we can't equal that. And I don't know. Theoretically, let's say we can. Okay? I don't know. Haven't been around that much temperature. All right.
It's all Greek to me.
It's all Greek.
I don't understand any of this stuff.
All right. So here's one more way to write this. Okay, what we're going to do is instead of an open dot, we're going to put a little round bracket, or we call that a soft bracket. Okay? And at 10 to the 32nd, if something is included, we're going to put a hard bracket, a square parenthesis looking thing. Okay? And that's how we're going to graph this range. Okay? Which brings us to our last notation called interval notation. And with interval notation, okay, we're going to take, we have two boundaries. We got the lowest possible number, and we got the highest possible number. We write down those two numbers, and if the number is included, we're going to put a square bracket on that side. If it's not included, we're going to put a round bracket. Okay? Hard bracket if the number is included, and a soft bracket. So take a look at these right here. Okay? And if we have 1 to 5, but they're not included, we're going to write 1 comma 5 with round brackets. That means they're not included. Okay? If we want to include 5, we're going to make a hard bracket. Okay? If we're going to include 1 hard bracket, so on and so forth. And then last little type, and then we're going to try some. If we say all x is bigger than 1, we're going to go to infinity. Okay? Okay? So let's try one real quickly. Take a look at that handout. Okay? Last little thing here, and then I'm going to have you try the first 5 here over the weekend. Can you tell me about the set of all numbers that makes this thing positive? What number could I put in for x that would make this positive?
1.
1. Good. How about 10?
Yes.
How about 0?
Yes.
Yeah.
How about negative 1?
Yes.
No.
Negative 1 squared is?
Yeah.
1. So this one turns out to be all real numbers. So let's graph that. We might do something like this and just kind of shade it in and put a big fat arrow. Okay. Anything on our number line? All right. Last thing is this. We're going to say all x's such that x is a real number. Okay? And we write this. Negative infinity to infinity. All right. I know that was super fast there. Okay, we're going to pick up with this on Monday. Think about the first 5 there. Okay, try them out. After you save your thing, you can go. All right. Thanks a lot, guys. There's some videos on the Night Math page too there if you want to look at that. But just think about it. Start the first 5. Give it a shot. Okay? See you later, guys. No. How do I save it or something? Go to open in. Make sure it's all pages. Right. And it should go for you. Say it. And it's done.
Oh, yeah.
You know what would be nice? A big box that's
Like making more drama than what it is. Like,
Got it completed. You're done. Okay? All right. So guys, just start 1 through 5. See what you can do with it and bring it back on Monday, okay? No sweat, no stress. Right? Get it?
This stuff is really hard.
Thank you.
Bye.
You too. Did it work all right for you girls?
Yeah.
All right, I know we just went real fast. See what you can do with these, incorrect, see what you can do with those, okay, and come back with something on Monday, okay? We got more to do, so don't stress too much about it, okay? All right. Not enough time today.
I think this is where we're a big loss
I lost you.
in high school.
That's right. Yeah.
It just,
Michaela Woodrum to the front office, please. Michaela
See you later.
Woodrum to the front
one
office.
is I didn't understand what they were really asking.
Right?
And the other, I think I didn't understand because it was like, why would you need to know this?
Right, right.
If you can give me a problem that we
Yeah.
can solve,
Yeah.
then I can understand.
Okay.
And a lot of this stuff is just foundation.
Yeah.
So how do you make it
Right,
You
right.
know, it's
That's
just
the challenge.
You just got to get through this and accept some of this.
Yeah. Well, we say we're talking about intervals, and so let's say you grow up someday to be a network guy, and you're trying to solve a problem, and you want to describe the range of times when. Thank you.
Yes. So, good news and bad news.
Okay.
All the Chromebooks are good first period.